All right, so it is week 7, and I'm going to dive into 242. It's been kind of a fun semester. I've been able to teach a bunch of different courses, so it's been kind of fun. Shifting gears here on Thursday. I'm just going to launch a new shell, so bear with me. Anyway, what I want to do today in lectures is talk a little bit about reports for 242. I know Tim gave you kind of a warm-up problem based on PV, and I've given you a few things to work on so far with, kinetic energy. Looked at flywheels. We've looked at Stirling engines. Last week I gave you a problem to work on for payback analysis of a solar thermal system. So we've been touching on a lot of different aspects here. But what I'd like to do now is just give you a good idea of what I'd like to see for your solar thermal report. A lot of you have come to me and said, I want to try this, I want to do that. I've got some folks working on a wind turbine here in the back of the classroom. I've had other people say, hey, I just want to work on a simple solar system. Others saying, hey, I'll do a solar shower. So any of them, as long as it's either a wind system or a solar thermal, I think we're going to have some great projects. So let's just look at the mechanics of the paper itself, what I'd like to see. So I'm just going to dig back into some old courses.
That paper for Tim's project or the paper for this class?
Well, Tim gave you a project, kind of a warm-up project for 242, so just knock that out. But your term project for 242 is what I'm going to focus on now. So I first started teaching this course in 2010, and it's like I don't have any papers from that year. So let's look into 2011. This is also back when we used to have electrical combined, and we've since just turned it into just solar thermal. Okay, so a lot of good papers here. I'm just going to start from the bottom. Metzger, that one's PV. Smith. Actually, let's not do that one. I'm going to find one that's. This might be a challenge because back in the day we were still doing solar PV standard service. If I can't find one, I'm just going to pause here for one quick sec. Give me a second. Okay, I found a pretty good one. This is Erica Allen from it's either 2011 or 2012, and. Or 2011. So this was from Erica Allen. She's was an online student in Chicago. So this looks fantastic. This looks perfect. Table of contents, list of tables, list of figures. I can show you how to do that shortly. She's got a nice title on there. Introduction to Site Analysis. So put this into your paper. Tell me where you are. Describe the property. You're going to throw some photos in there. We'll see those shortly. Describe it quantitatively. How big is the house? She actually went into the Department of Energy, looked to see what their suggestions are. She's got it bulletized. You can see my little comments here. move this guy or not? Okay. Yeah. You live in an area with an average annual wind speeds of at least 4.5 meters per second. And this is going to be true in Chicago for sure. Now, here's the other issue here. The economics of renewables are going to change, I think, pretty quickly. And I think just saying, oh, my average wind speed is 4, I can't do wind, I don't think it's a valid argument. It's really not. And again, I'll go back to this analogy of the guy digging a hole, and he gets some dirt on his shovel. He's like, oh, what do? Do I go back and get some more dirt on my shovel? No. Like, some dirt is better than no dirt. Just like, keep digging. That's the best I can do. And again, I just wouldn't necessarily base it purely on economics. Now, if you're going to evaluate wind versus solar, sure, then do the economics. But if you're just evaluating, oh, I'm just going to keep paying for non-renewables forever versus doing my renewable now, I think the choice is pretty clear. Maybe it's just personal bias, but there it is. And so that's fine to put that data in. You've done your homework and you've got the numbers.
Well, it'd be great if you had viable dump load, you know what I'm saying? For when it did get more than 4.5.
Sure, viable dump.
Somewhere to put that energy.
Yeah, and a good place to put your dump load would just be a heater. If it's blowing hard in the winter, just heat the house.
Or air conditioner.
Or an air conditioner, but blowing hard, cool the summer, in the winter. Or,
I was thinking heat the swimming pool.
yeah, what you might do, I mean, especially now, I mean, all these were written before the Tesla home battery system was out. We can take another good dump load would just be your car, your electric vehicle.
Speaking of electric vehicle, do we have that battery ordered? That's the only problem, isn't it? Was the battery, right?
I'm hoping Lee might be working on that. Yeah. Okay, so here are a few home battery kits. There's Outback, there's Solar Edge. Here's the Powerwall, the Tesla home battery. So, well, that's news. March 18th, 2016. Hang on. Tesla discontinues. February 2nd. Huh. Well, you might look into one of these too. Mercedes.
Discontinued?
I don't know, that's what it says in the news.
10 kilowatt Powerwall whole battery.
Well, let's take a look. Let's see what this comes up with. Okay, so there's something for daily cycling.
They've just downsized.
Yeah. This, I did not know this. The thing only cycles 500 times. Hey, what's going on?
Yeah, in other words, you better make sure that thing is totally dry before you start powering it back up again.
Yeah.
You only got 500 times to hook the charger to it.
That's a new one on me. I didn't know it was going to be that wimpy. Lead acid batteries, of course, thousands of cycles. Well, you know what? They went for it. But my point is here, on your report, I would like just, go and find what's available retail. And apparently, if Tesla still has something out there, shop around, do a price comparison, and what I would suggest you do is a units conversion and just see what each one costs. See what each one costs both on a, so the cost function you want to come out with is like so. So we can do it like this. So if you're doing your battery research, let's just call it Technology 1, Technology 2, Technology 3. Here's going to be your capacity. And we'll put that in kilowatt hours. And let's just say this one's 10, this one's 15, this one's 5. And then let's just look at a price. Let's just say this guy is I'm just going to make this price. I'm going to put it in dollars. And shoot, I don't know, let's just say this one's $2,000. Let's just say this one is $3,500. And let's say this one is $750. So I'm just making these up. Come in and do a control 1. Currency, get rid of those. That looks better. Take these home, center them up. Okay, and now you're looking at, what would you call this, just value. We'll put this in dollars per kilowatt hour. And now I'm going to see, so this is just equals dollar divided by capacity, dink, dink. Okay, so from there, this just allows you very quickly to compare these guys. Now if I come in here, grab this, let's see if this works or not. Insert, let's just insert a bar chart. I think that worked. Oops. Yeah, we can actually do this. So we can get rid of, we'll get rid of price, and we can plot value. Actually, no. I think we can just get rid of format data series. No, not that one. Select data. I'm going to get rid of capacity and price. There we go. So what we're looking for is the best bang for your buck. So even you're like, oh shoot, this guy is too small, but it's the least expensive on a dollars per kilowatts. This is the one you would perhaps purchase. Now the next factor. And this is something that I just realized, 1,000 cycles on the lead acid versus 500 on the Tesla. So we can put that in as another independent variable in Excel. So let's do that.
Why would somebody want to buy a Tesla battery?
Well, you brought the point of I want a dump load. The wind is blowing at night, but nothing's on, and rather than just letting that go off as heat or nothing, I'm banking it.
No. I mean, the point is, why would you buy a Tesla battery over just a conventional one if you're not getting as many charges?
I don't know, but that's the question we're trying to answer here.
Oh,
I mean, it could be that the Tesla battery is, maybe it's way cheaper, I don't know what the price is, and it's more like a disposable deal where you just keep buying it. Like, I'm gonna go buy a Bic razor instead of the Gillette.
$1,500 more.
Well, yeah, so,
That's what I'm,
Okay.
that's what I'm getting at.
Gotcha,
There's gotta
yeah.
be some sort of, maybe the battery's got a built-in converter in it that ships everything off to your dump load.
Right.
The regular battery just got, just the batteries.
could be, and then when you're looking at them, there could be other factors, like compatibility, what have you. So if we go up here and say, well, let's look at the number of cycles. And let's just say technology 1 is, let's just put that in as 500. Let's put this one in at 5,000, for example. And let's just say this guy is, I don't know, somewhere in between 2,500. So what you're actually buying are the total number of kilowatt hours this thing's going to store, which is the number of cycles times the kilowatt hours per storage. So now we have this capacity total, because you're filling up the jug this many times, so equals single capacity times number of cycles, et cetera, et cetera. So now we're going to do value total, like the total value, not value per cycle. This is again going to be dollars per kilowatt hour. So again, this equals the price divided by the total. Okay. And then just take this, we can just take this chart, copy it, paste it, and let's see if I'm looking at, yeah, so let's just take this and drag it over here. Let's see how this works out. Take this one, drag it over here.
Couldn't you just grab them all at the same time?
Well, I could, but I wasn't able to click on them.
Oh,
I could have just started from scratch too.
Isn't that the one in the middle?
What's that?
Isn't that the one you're trying to switch over?
No, I got these other. I got the top two. The other one's two. The other one's two. Okay, hang on. If I click on value, actually, I'll just start over. So let's just do the whole thing again. Insert chart columns, and now I can select data, get rid of capacity, price, value, capacity total, and all we want is the value total. So whereas Tech 3 was the best bang for your buck on a single charge, Tech 2 came out slightly better over the lifetime. So that's something to consider too. So this is the kind of, research that you're going to do, because this is the research you would do for your customer anyway. Hey, I'm going to put in this battery, and they're going to ask you the question, why? Well, look how it performs. Look how it performs over time. And maybe they've got a better policy where they take it back and recycle it when they're done, rather than you having to scrap it or landfill it. Okay. Okay, local building codes or covenants allow you to legally erect a wind turbine on your property. It's a little nebulous here in Missoula. That's one reason why we put put our wind turbine up on a trailer. It's not on a building.
Can't put
It's,
it on
it's,
building?
it's fenced in. It's a good question. It keeps coming up and keeps coming up. There are a couple wind turbines in town. They aren't giant. They don't stick up in the air that high. But there've been some issues over the code, and I don't know exactly what it is at this point. You're comfortable with your long-term investments. I think another big part of it too, there's an off-grid house in Billings, and the guy's got a vertical axis wind turbine right in his front yard. And he just went and talked to his neighbors first. It's the same thing with covenants. Hey, I'm gonna build a fence. Is that okay with you? Sure, build your fence. Or, so that's a big part of it too. So what Eric is proposing, 800 to 1,000 watt turbine, uses a backup system. She's in the city, very difficult to be off grid using just wind. That's true. I mean, 800 to 1,000 watts, that's the average electrical load for a house, and the thing would have to be running all the time to supply the electricity. Just not going to happen. She's done a little bit of research. Selected the Eddy GT, provides everything required to make the system work. Heavy duty, solid, but it's expensive. Well, probably worth it because that's going to reduce your maintenance costs. That's another thing you could put into your chart. What are the maintenance costs? That's going to add. Well, it's going to subtract from your dollars per kilowatt hour. So you can put that in as well. 1,100 watts and 35 mile per hour 35 mile per hour winds, 56 pounds. It can survive 105 miles per hour. Also very good to know what are the limits of the technology. There's the front of the house. Here's the west side. Load analysis. Let me make this just, oh, there we go, a little bit bigger. There's the average wind speed, so this is how much energy I might expect to get. What I don't see in here, and what you would want to show, what you're going to want to show, if you're designing a wind turbine, or purchasing a wind turbine, you're going to want to get this from the manufacturer. And this is an absolute necessity, is that you get, well, you get power as a function of wind speed. And it's going to do something like this. Right, and for the one we were looking at, here's, 1,100 watts, and here's 35 miles per hour, and this will allow you to estimate how much energy you will get from it based on the wind speed. So, a histogram comes in. It could be that the majority of your wind. So if we just do 5, 10, 15, 20, 25, 30. You would then build a histogram. Chances are most of the time the wind is not blowing at 35 miles per hour. Might blow at 30 a little more frequently, 25 a little more, 20 perhaps a little more. So this is kind of what we're looking at in terms of estimating the total wind. So here's basically 0 to 5 miles per hour. This is most of the time. Every one of these boxes. Let's just call it. Let's see what's a good name for this. V5. This will be V10, V15. All the velocities between 10 and 15. V20, V25, V30. Sorry, 5, 10, 15, 20, 25, 30, V35, I guess I skipped a box there. Let's just put that all in one big kind of box between 30 and 35. The sum of all of these V 5 to V35 equals 100%. So, for example, if V20, let's just see if this guy could be, what's a good round number? If this is 20% of the 20% of the time, the wind is blowing between 0 and 5 miles per hour. Well, you're going to multiply that by 0 because your turbine doesn't function at that rate, right? Let's just say this is 15% of the time. Well, that's okay. So 15% of the time, you're running at a velocity between 5 and 10, and the average power, let's just make something up, is 15 watts. So you would multiply 15%, let's just go ahead and do that.
Use a left-hand summation on that, wouldn't
I would just grab the average.
Just the average.
Just assume that that's a line through there, grab the average. So 15%, let's just see how much energy we're going to get from this wind turbine if the wind, and this is going to be rated in watts, the wind is blowing 15% of the time between a value of 5 and 10 miles per hour, and that's a 15-watt output. So let's just let that happen for a full year. How many kilowatt hours are we going to get from that guy? And then we can just repeat the exercise for the rest of the curve. Okay, so let's just do it in seconds. So we're doing 60 times 60, so 60 seconds times 60 seconds, 60 seconds per minute. Times 60 minutes per hour times 24 hours per day times 365 hours per year. This is going to equal, let's just run that number really quick. So 60 times 60 times 24 times 365 equals, what was that, 31 million seconds? 32 million seconds? Yeah. So 32 times 10 to the 6th seconds per year. Okay, now the turbine is going to give you 15 watts for 15% of those seconds. So energy equals power times time times let's just call this I'll just call it V10. Right? So, what's the power? 15 watts. What's the time? 32 times 10 to the 6th. What's the fraction? 15%. Okay, so that's the number of seconds per year times 0.15, because only 15% of the time is the wind blowing that hard, equals times 15 watts equals 71 megajoules. 71 watt, 71 times 10 to the 6th watt seconds equals 71 megajoules per year, watt seconds per year. And what's the conversion from megajoules to kilowatt hours? 3.6. 1 kilowatt hour is 3.6 megajoules. It's a good one to know.
So I was wondering how you were doing that conversion from just megawatts to megajoules.
So kilowatt hours. 1 kilowatt hour is 3.6 megajoules.
So when you just multiply that, 71 times 3, 3.6?
Yes, let's just do it this way. The way I always like to write it out like this. 71 megajoules. And again, we know that this way there's almost no confusion. 1 kilowatt is 3.6 megajoules. 1 kilowatt hour is 3.6 megajoules. So 71 divided by 3.6. Yes, we're looking at 20 kilowatt hours. Not very much. It's like a day's worth of power of the whole year. Okay, but now if we get up into these greater amounts, let's just say right here we're actually at 500 watts, and we do this V25, and let's just say this is something like 8%. You can then rerun that number, right? So you're going to have, this number is going to be, well, I'll just do it. So this is going to be this is going to be E10, E25, E25 equals, what did I say, 500 watts? Yeah, 500. So already we've gone up quite a bit. We're going to start off that same 32 million seconds per year, and we're now at 8%, 0.08. So let's just run that really quick. So 500 times 32. And I'm just going to leave the 10 to the 6th off, so we're just going to run this in megajoules, basically, times 0.08 equals, so I went from 71 to 1,200. And now I divide that by my 3.6, 355, right?
Which you put in 47.
Yeah, exactly. So now I got that's actually kilowatt hours, because I already divided by the 3.6. So so E25 equals 355. Okay, so what we've done here, we've calculated the V5, we know just equals 0. The V10 equals 20. Et cetera, et cetera. We know that the V25 equals 355. So, in order to calculate the full performance of this wind turbine at this calculation, You just need to know what the wind is doing. Again, these little V blocks are what the wind looks like in your particular location. And then you just need to know what this performance curve is of the turbine. How many watts come out for a given velocity. So what we just did, we multiplied these two curves by each other. One was continuous, but we just chopped it up into discrete variables. We laid the wind profile over the top of it and just multiplied the boxes by each other.
That's why when I was looking at that, I thought the boxes would go the other way.
No, this is just telling you that most of the time the wind is not blowing. Most of the time the wind is not blowing. And, maybe, just you get out to here and maybe, gosh, we'll just say 3% of the time the wind is blowing, 30 miles an hour or greater. And you're going to get a lot of power up here, but it's just not going to happen for very much time. So that's how to do that problem. That'd be a fantastic quiz problem for this week.
Don't do it, man.
Don't.
Don't do it, man. I'll break out my integrals on you. I'm just thinking about how to do that in an integral at the moment, in fact.
Well, if you wanted to run this as an integral,
Integrals, I'm sorry.
I know, I'm just kidding. If you wanted to run this as an integral, this would have to have some function, and it would actually be you can run as either a dot product or a convolution, but no need. It's not that complicated of a problem. You'd break it out into these 7 or 8 blocks, pick a point off each one, and just set this up in Excel. So you could, easily set that bad boy up in Excel. We could just do that really quick even. Wind. So I guess the way I would run it, and here's your V's. And I'll just write it out as V5. And something like this could go right into your report. 10, 15, 20, 25, 30. So come down here, this becomes 10. This becomes 15. This becomes 20. This becomes 25. This becomes 30. And then here's your power. So your power is going to be, we'll make these up. They'll be 15. Let's just make this guy at 50. Now this is actually going to be a cubic function in general. Wind turbine power is a cubic function of velocity. 200, 500, 1100.
In other words, the polynomial describing the integral would be cubic.
Yeah, it would. Yeah.
The function is.
Yeah, it would be. That's exactly right. Yeah. And the way I've drawn it here, the practically, so this would start out as a cubic curve. It's going to max out at some point though. It's just not going to keep going up forever. At some point it's going to feather so it doesn't blow itself apart. At some point the mechanics are just going to overwhelm the electronics. It's not going to be able to suck electrons through that quick. And at some point the mechanics of the wind are going to overwhelm the mechanics of the turbine. Like the blade's going to come off. Up in Browning, every time we go up there, there's another blade missing off one of their wind turbines. It's just ferocious wind up there.
Yeah, well, it just happened. I mean, that's why they got brakes on those, so they don't exceed that.
Yeah.
In other words, the wind could be blowing hurricane force gale out there and you can't ever activate your wind
No.
turbine to.
Yeah. It's like, hey, Barney, let's go and set our wind turbine up in Hurricane Matthew. There's a lot of energy there, I hear.
A
Yeah.
couple times and then go. I've seen the Wizard of Oz. I actually, I don't know, it was a Facebook post. There was a windmill, I don't know where it happened, but somebody was recording it, and the next thing you know, you could see it, one of the fans started cocking off sideways,
Yeah,
then the other one cocked off, and then the thing exploded.
yeah.
It was, and, I mean, it's not just one of these little, trailer windmills, I mean, it's one of the big ones.
Hmm.
It's another thing, I got, and I tried to get a picture, but my wife took a videotape of it when we were going to Colorado a couple weeks ago.
Yeah,
We left out of here, and there were 2 trains, and I don't know how many cars, but every 2 cars, there was a windmill
Yeah.
turbine on it.
yeah,
And they were going that way.
yeah.
From Seattle. There was 2 trains and they were huge. So I don't know how many fans there were on it, so.
It
It
happens.
has to be at least 30.
Yeah, I know Obama launched some, big manufacturing deal a few years ago. They were building turbine blades in Ohio or Pennsylvania, whatever it
These
was.
are over in Seattle, aren't they? Over by
Well,
Boulder,
which direction were the blades going, east or west?
that way.
They were heading from the west to the
Yeah,
east?
to the east.
Oh, so maybe they were manufactured in Seattle.
So I was thinking.
They could also be manufactured in China. They're just coming.
On
Who
the
knows?
boat,
Yeah.
Off the boat, yeah.
I know Spain also does a lot of wind turbine manufacturing. Okay, so what I've done here, this is just the percentage of each one, and I just made sure that they added up to 1. And then this is the power, so I just used F as a fraction, so you could put that as a, percentage if you like. And then here's the power in watts. And let's just come in and do the time. And what we say, this equals 60 times 60 times 24 times 365. This is seconds per year. Throw a control 1 at that guy, number, ding, ding, comma. Nice, okay. So, let's go back to our formula. You like the sound effects?
Yeah,
Yeah.
a little underwear non sound effects.
So, we've got the watts times the time times the fraction. So we're gonna put this in watt seconds per year. So this is energy, which is in watt seconds per year. All right, so equals power times time, and I'm going to throw that dollar sign in front of this. This will keep it as an absolute reference. Times our fraction. 0, yeah, sorry, well, 0 times anything is 0. We drag this down, and now I'll put this copy, paste, energy in so a watt second is the same as a joule, so I'll just put this, we're going to multiply this, so I'm going to convert it to megajoules, and to do so, this equals that number divided by 1E6, which is a million. Still 0. Too bad, sorry. And let's see, control 1, number, Get rid of the decimals, throw in a comma. Okay, okay. So that's not too bad. I mean, this is a little surprising. I mean, you're,
Can I
what,
back you up? Can you
Please.
go to G7?
G7.
Punch into G7 again so I can see that formula.
Yeah, yeah. So I'm multiplying power, which is in F7, times time, which is in B. So power times time is energy, times the percentage. And remember, these percentages all have to add up to 1. So I just made sure that I've accounted for all of the seconds in the year.
Well, I was looking at the 200, the 18% of 200, and I wasn't seeing how you could get 140.
Well, the reason the numbers are so big is because I'm using seconds, yeah. And that's why you come in and divide it by 1,000,000, and now it makes more sense. Now we'll take it again, copy, paste, so it'll now be in kilowatt hours per year. So equals that divided by 3.6.
Still zero, damn it.
Darn! Still 0. So there's your kilowatt hours per year. Now we just sum it up. So we can take that guy, copy it, paste it, Control 1, number, bam, bam, comma, ding, okay, save. And let's look at the cost. So dollars per kilowatt hour. You can just do this as a payback. So let's just say for whatever reason your dollars per kilowatt hour is like super cheap somewhere, a little more expensive somewhere else, 1.5. Now we're getting out into California. Now we're kind of out in Hawaii. Now we're up, I don't know, in Alaska somewhere.
Price of
Dollars per kilowatt hour. So dollars of electricity per year equals that many kilowatt hours, and we'll pin that same cell, times, so it's the kilowatt hours times $1 per kilowatt hour. Control 1, this is going to be currency. Okay, so if you're paying 6 cents, you're making $91 of electricity a year. If you're paying 75 cents a kilowatt hour, you're making $1,100 worth of electricity per year. Control 1, currency, bam. So let's see, what was the initial cost of this technology? It's an 1,100 kilowatt turbine. Probably by the time all is said and done, inverter installation, it might be a $10,000 gizmo.
So I was going to say, is it about $100 a kilowatt hour?
If you can get $10 a watt, $5 a watt, you're doing pretty well. So I'm just going to throw up the capital cost. I'm just going to say it's 10 grand. $10,000, currency, dink, dink. Years to pay back. How do you like that for an acronym? Equals capital cost divided by dollars saved. And again, on that B9, I'm going to pin that. 110 years, I'm going to be dead by then. Versus 8 years. Okay, so this is when people say, oh, it doesn't pencil. Well, maybe, maybe not.
I don't know, I'm thinking on average, a person, I know for me, I'm paying on my little freaking apartment, which is just unreal. I'm paying nearly $1,000 a year for just to heat it.
Yeah, yeah, yeah. So,
You know, that's because I heat with my little cat door open up and my cat goes in and out and a little door that's.
yeah, and I think what we're finding here is if you have a renewable energy technology on your house, the value of the house goes up. Like, it doesn't go away. Like, it will pay itself back the second you sell it. So the years to payback become however long you own the technology sitting in your house for. So, anyway, that's, I don't know how, that just took me, 20, 30 minutes, but that's the bread and butter of any energy technology right there. And we just did it for, kind of simple residential wind system. To this, you could add, maybe you've got a tax incentive. Maybe you're actually pulling in renewable energy credits, carbon credits, and then all of a sudden these numbers go down even further. So, all right, I'm going to take a break because that was a lot. That was a lot, but it was good.